everyone. Thank you so much for joining us here. I am Melliyal Annamalai, a product manager with Oracle, and I'm very excited to talk to you about graph databases and graph analytics. So what I'm hoping to do in this session is to talk about all the insights you can get into your data when you model your data as a graph and analyze the connections that exist in your data. So graph is a data model that helps you look at your data from the point of view of connections in your data. Almost any data set can be modeled as a graph because any data set naturally has connections between the different data entities. And we'll walk through a few examples in this session. So graphs allow you to analyze your data using graph algorithms applied to your graph model and allow you to ask queries based on these patterns that analyze the connections in your data. And this has applicability in a variety of industries. And we have customers who use graphs in the financial services industry, manufacturing, public sector, telecommunications, and so on. And I will be sharing some of those examples with you. So any data set has logical connections between its data entities. So let's take the example at the top, where you have a bank accounts table and a bank transactions table. The bank accounts table contains information about bank accounts. So each row represents a bank account, and the columns in the table have information about those accounts. So this your bank account is a data entity in your data. So this is what we would call a vertex table, and every row in this table becomes a vertex in your graph. Then you have the bank transactions table, which represents relationships between two accounts, as in when there's a cash transfer between one account to another, that becomes a relationship between the two accounts. So this is a logical relationship that can be represented by an edge in the graph. So you can see here that in this simple data set, you have vertices, you have edges. So the bank transactions represent the edges, it's what we call the edge table, and the bank accounts is the vertex table. And then in the second example, in the second half of the slide, we have three tables: customer, rented, movie. The customer table contains information about customers, the movie table contains information about movies, and the rented table contains information about which customer rented which movie. So you can represent customers, which are naturally data entities, as vertices in your graph. Movies are also vertices in your graph. So you have two types of vertices in this graph. And then you have rented as the relationship between these two different types of vertices. So when a customer rents a movie, that becomes an edge in the graph. So you could represent your graph this way to then see whether you can cluster customers using some graph clustering algorithms to identify what movies you could recommend for a particular customer and so on. And we have several interesting examples coming up. So first, let me highlight where graphs add value. So in financial transactions, like the example we were just looking at, when you have cash transfer relationships representing edges, it gives you many different tools to identify whether there is fraud in a financial transaction. For example, if you have a set of cash transfer edges that form a cycle, that is perhaps something to investigate further, because when cash moves around in a cycle, it can maybe represent money laundering. That is money, let's say your cash transfer starts with account A, goes to account B, then C, to D, and then comes back to A. That's a cycle. Then you can use graph analytics algorithm on your bank graph to identify which accounts have many transactions flowing through them. So an algorithm like PageRank, for instance, which identifies in a graph which are the vertices that are important, which in this case would mean which are the vertices that have a high number of transactions flowing through them. That may be an account you want to flag as well for the purposes of detecting fraud. And maybe there are some unusual patterns in this cash transfer graph that you're building up that can flag you, that can be a flag that you need to, that can alert you to accounts and cash transfers that you need to investigate more closely. So these graph patterns and graph analytics algorithms can give you new insights that are not easily possible using other methods. In manufacturing, we have bill of materials that naturally form a graph and can be used to find indirect connections between components. For example, you might want to do a what-if evaluation. What happens if you change the design of a particular component? What is the impact on all the other components in my bill of materials? Or I want to uncover new connections because I've linked components from different domains, and I can do a path analysis in a graph to identify that these components are connected. And then customer communities, as I was saying earlier, can I identify clusters of customers that have similar behavioral patterns by analyzing the graph that helps me make better product recommendations to my customers? These are just a few of the business problems that can be solved with the help of graph analytics and where graphs add a lot of value. So let's look closely at the financial services fraud detection example. We go back to our bank accounts table and a bank transactions table. And every time there's a cash transfer between two accounts, there's an edge. And let's look at here a screenshot from a Graph Studio product, which identifies that there are cycles. Like, is there a cycle 4 hops long that passes through account 934? And yes, there are 3 cycles that are 4 hops long that pass through account 934. And when you ask queries like this, you can have very sophisticated, you can uncover sophisticated patterns. For example, here is an example from one of our customers where they found that there were lots of cash transfers between 2 accounts, but they were going through a lot of intermediate accounts. So the same source, the same destination, but lots of intermediate accounts. So this could be some way to try to prevent prevent. It could be some kind of money laundering, or maybe you want to detect evade detection. Instead of having a direct transfer between 2 accounts, you're going through multiple accounts and so on. And in the screenshot on the right, it's once again lots of accounts, but relatively few source and destination accounts when it comes to cash transfers. So these are anomalous patterns that you can identify or uncover by running graph queries, and we'll be seeing a few examples of that as well. And then this is something that alerts you to specific accounts that you need to investigate further. Another example from the financial services industry is, again, modeling their customers as vertices, and then any relationship that they uncover based on customer behavior as an edge. For example, if 2 customers use the credit card within a few seconds of each other at the same establishment, these might be 2 friends having lunch together. That's a social activity. So maybe these two people are related to each other in some way. So maybe I'll add an edge between them. So you build up your graph in this way. You have your customers as vertices, you have any activities together and any other observations you make of them together become edges, and you build up your graph this way. And then you can run clustering algorithms to identify customers who have similar interests and similar incomes. And this gives customers a much richer view of their data, because you can identify similar customers by many different techniques. And this gives a new dimension and more accuracy in identifying customers who are similar to each other. And this particular customer has a very large graph of 400 billion vertices and 2 billion edges. In manufacturing, like I said, bill of materials is one example. And another example is connecting components across different domains. So here I have 3 different domains. And I have my objective is to see whether whether components in these 3 domains are connected to each other. So you can see here that A1 is connected to B3, and that's all I might know. I might know that A1 is connected to B3. But separate from that is the information that B3 is connected to B5, and B5 is connected to C1. Now, when I connect all of this in a graph and do path analysis, I can get the entire path that A1 is connected to B3, B3 is connected to B5, and B5 is connected to C2. So I can see that B5 and C2 also have an impact, could have an impact on A1, not just B3. So I can, by following paths through multiple different domains and multiple different components, I get a richer view into my data. So the same manufacturing customer could identify highly connected components by running the PageRank algorithm on the graph. And what this tells them is which are the components which are used by many other components. So, or which are the components that many other components depend on. So the PageRank value tells them which are highly connected, which gives them these insights. And you can also cluster these nodes to identify, for example, which are the components that are most often used together. Clustering really helps you do that. Which are the components that are often combined together in a larger component and so on. So modeling your data as a graph helps you uncover these hidden connections and apply this interesting graph algorithms. So the ability to do all this and more is available as part of Oracle Graph, a feature of Oracle Database that builds on the Oracle Database capabilities of extreme scalability, high-speed transactional or data warehouse applications, the ability to support these kinds of applications, concurrency, fine-grained security, high availability, and so on. So as you might have seen in other sessions, the Oracle Converse database includes support for many different data types like JSON, documents, spatial, and graph as well. So the Oracle database is a complete graph database for the enterprise. And I know some folks out there might think that, oh, Oracle is a relational database, but Oracle has really evolved over the years. And there are so many different data structures and so many different things that are built into the database now to make all kinds of workloads extremely fast. So when it comes to the graph features, we have comprehensive set for graph analytics. I mentioned the PageRank algorithm, clustering algorithm, and we have support for over 60 natively implemented graph analytics algorithms. We natively support two graph models, the property graph model and the RDF graph model. And I think I'll come to that in a second about the differences between them. We are always being standards compliant, so we support standard languages such as the Sparkle query language from the W3C. And for the property graph query language, we don't have standards yet. The SQL PGQ standard is expected soon, and we plan to support that. Meanwhile, we're supporting the PGQL language, which is property graph query language that is aligned as much as possible with the SQL PGQ standard that is coming out. We have Java and Python APIs to do all of these graph operations, create a graph, query a graph. Like you can take this Sparkle or PGQL query and embed it in a Java API, so you can include it in your application. Same thing with Python. You can also work with these query languages using popular tools like SQL Developer, SQL CL, Jupyter Notebook, and so on. And the very interesting feature, especially when it comes to a property graph support, is the ability to create graph views on our relational data. So you don't have to move your data into a separate siloed database. You don't have to take your data out of the database. You don't have to take your critical business data even into another schema. You can leave the data where it resides in your database and create a property graph view on this data. You can load this into high-speed in-memory graph server as needed, but you can do a lot of operations on your graph view of your data. So rather than moving your data to where your graph analytics are, you can bring your graph queries and graph analytics right to where the data resides. So, and that brings me to graphs and transactional workloads. So because our graph feature is so integrated with the database, we can work with any workload that requires transactional consistency. You can have streaming data, you can have high-speed updates for your graph, and you can be simultaneously querying the graph. Graph queries will always see the latest data, which that is transactionally consistent. You can also, the database also supports a very high degree of concurrency. You can have thousands or tens of thousands of clients that can be inserting and updating your graph in parallel, and you can be querying the graph at the same time. And Oracle Graph would scale well and work well. So I think that is one of the unique features that we've built on the of decades of mature transactional consistency capabilities that the Oracle database has. So I mentioned the two graph models, the property graph model and the RDF graph model. See, graphs have been around for a while. Folks have been looking at graphs because it is a nice way of modeling your data based on the connections in your data. So the RDF graph model has been around for the last 15 or 17 years or so, and is widely used in linked open data kind of applications because it has the structures to make it easy to connect data from different sources. And it's used, and increasingly it's been used in knowledge graph applications where you're representing information in a domain as an ontology, and you want to include that in your data. You want to infer new facts from existing data, and so on. The property graph data model is relatively newer and is getting a lot of interest because of graph analytics capabilities, like the ability to apply algorithms such as PageRank and clustering and path analysis and so on. And the examples that I talked about are mostly around property graphs, like identifying fraud, modeling bill of materials for in manufacturing, and so on. And the rest of this session, I'm mostly going to be focused on property graphs. So property graphs are really very relevant when it comes to graph analytics and getting new insights in your data. And I will again say that we support both graph models. So I talked about scalability. So here are some real numbers from some of our customers. The first one is an RDF example. The National Statistics Center in Japan has, this is over a year ago actually, where they had 2.1 billion triples. And the year before that, they had about 1.1 billion triples. And the performance has remained the same as the data size grows, about 1.27 seconds average Sparkle query response time. And Kesha Bank has another large graph, and they've been able to use graph analysis for real-time transaction monitoring. So you can see here that the scalability that we bring to graph databases and graph analytics. So when you talk about property graphs, and that's what I'm going to show some examples of how you would actually use some of these features. So just wanted to emphasize once again that you have graph queries and graph analytics as the two key ways in which you can analyze your data as a graph. And when it comes to graph queries, you're looking for paths, different kinds of paths, complex patterns, cycles, and graph analytics algorithms. We have many different algorithms that you can use. So when you're working with property graphs, how do you get started? You first need to create your graph. You have your tables. I mentioned that you can have a property graph view of data in your tables. So you need to create a graph from your tables. You then need to query this graph. And then you can apply analytics algorithms on this graph. And then with graphs, it's always very interesting to visualize the results. So that becomes an important component as well. So let's see how you would create a graph. And let's go back to the bank accounts and bank transactions table. So here is where we are going to represent every account as a vertex. And every time there's a cash transfer between them, that becomes an edge. And I mentioned that the bank account is a vertex table, the bank transactions is an edge table. And here is an example from the property graph query language for creating a graph from these tables. So I'm specifying here the vertex table, I'm listing bank account as a vertex table, I'm listing bank transactions as an edge table here, and I'm mentioning the source and destination for these edges, and so on. So it's quite intuitive and straightforward to look at your table database schema, identify your vertex and edge tables, and then set up the create property graph statement in the property graph query language to run some queries. So after that, you want to query your graph, and that brings us to the property graph query language, which is a SQL-like language which selects from and where clause and other constructs, and in addition has a match clause to specify graph patterns. Like if you want to specify a cycle, If you want to specify a path of length 4 or of unknown length, you need a way syntax. You need the syntax to specify the graph path. And that's what the match clause allows you to do. So here is this, in the first example, is this query, which is just saying select edges from a graph. So it's like saying select star from tab. So I can select edges from a graph and I can visualize this in the cycle. The second one here is a different, it's a more sophisticated query where you're saying match any edge that has a label transfer that is 1 to 5 hops long. So start from vertex A and traverse 1 to 5 hops from vertex A and start with ID 534. So I'm starting with ID 534 and I'm traversing 1 to 5 hops. So finding all paths that are 1 to 5 hops away from A, and also as a cycle, because I'm again saying ID A equals ID B. So I'm starting with 534 and I'm ending with B, which I want A to be equal to B. So I'm basically saying, find me all cycles that are 1 to 5 hops long. And here's a cycle that is 3 hops long. And here I'm saying, I'm giving A vertex ID 934, B vertex ID 387. And I'm saying, find me all paths between 934 and 387 that are 1 or more hops long. The plus indicates 1 or more hops. And the one row per step is just a way to visualize the intermediate nodes in the graph. And here I'm saying, find me the top 5 shortest paths. Once again, I'm looking at A and B as being 934 and 387. And I'm saying, find me the top 5 shortest paths between them. So you can see here that you can do sophisticated path analysis. You can find cycles, you can find any path between 2 accounts, you can find paths that are 1 or more hops long, you can find the shortest paths, and so on. And finally, here is an example where I've run the PageRank algorithm, and then I want to find out the PageRank value for the different vertices in the graph. And I can display that as a table. So the result of a graph query doesn't only have to be a visual representation of the result, it can also be just a tabular representation that is used in other parts of your application. And you can run these queries using SQL CL, SQL Developer, or in any application that you're working with using Java or Python. And that was a graph query. And when it comes to graph algorithms, you can run over 60 algorithms out of the box, like the clustering, ranking and walking, that's finding important vertices, like PageRank and all the variations around that. Finding paths, there are many different ways of finding paths, shortest path and so on. There are some machine learning graph algorithms and other algorithms to detect structures in a graph. So you have many different algorithms to analyze the entire graph and how the data entities are related to each other. And all of these are invoked by simple API calls after loading the graph into the graph server. So here you can say the read graph by name loads the graph into the graph server from the property graph view. And then you run an algorithm here, like say PageRank. It runs an, or you would say between a centrality, you would run whichever algorithm that you want to run, you just invoke that with a simple API call. And this application development is with Java or Python APIs. So I talked about graphs, I talked about why graphs are useful, I talked about graphs queries and graph analytics. Let's see how easily you can do all of these operations when you're using the Graph Studio feature of Autonomous Database. So in the Graph Studio feature, we have an automated graph modeler to help you model your graph. So this automated modeler will look at the foreign key information and the primary key information to identify the vertex and edge tables and propose a model to you for a graph. It has a notebook UI for running graph queries using PGQL, for running graph analytics algorithms, and so on. And the notebook includes some integrated visualization. It's really easy to provision. When you provision the Autonomous Database, you have the access to Graph Studio, and it's a fully managed service. So let's take a look at what some of this looks like. So we want to model and create a graph. Here I am now selecting the tables that I want to include in my graph. And I've selected, it has identified that the bank account and the bank transactions table or the vertex and edge tables respectively. I can change the labels of these edges and vertices. I can change the direction of the edges as I'm doing there. I can look at the source. I can do a preview. So all of this is point and click. So you look at the list of tables that you have. It proposes a model. You can make some changes using this interface like I'm making right now. And then I can say create graph. I can type in the name of a graph. And then I can type in the name of a model. The model just represents the underpinnings of how the graph is connected. And then I click on create. If I don't want to load into memory right away, I turn that off, and then I create the graph. And the graph is getting created. So that is a simple way to create a graph. So it's very simple to create a graph. So let's see how we can now analyze that graph, query analyze a graph. So here now I'm looking at the graph. I load it into memory, and then I click on my bank graph notebook to run some queries. So first, the environment is initialized. So then I can start running some memories. I can programmatically load the graph into memory if I wish to do that. And it'll tell me if the graph is already loaded, as it is saying that right now, because I did load the graph earlier. And then I'm running that query, which I said was a select star from tab, a simple query. And so this gives you a feeling for the network, or sorry, the notebook and the graph, and you can right click on any account to see what's in there. And here are some of the queries that we were running. So you can see here that you have a nice notebook interface for easy development, and you can very quickly get started with using graphs. So let me just finish off by saying why Oracle Graph. Once again, scalability to billions of nodes and edges. It's a graph database for the enterprise, the lower operational cost and lower risk, and lower development effort. You can see here that it was really easy to get started with graphs. You provision your autonomous database, you have Graph Studio, you support all standards, you can easily move applications from different databases onto this database, and we use all the popular languages and development frameworks. You can also work with Java and Python clients. You can work with Jupyter. If you're using an on-premises database, it's available there as well. So Oracle Graph is available in any database edition on any platform. So some of the planned features are, in an upcoming database release, we plan to support the standard, like I said, the SQL PTQ standard, that allows you to do this in SQL. Like all the examples I was showing you was in the property graph query language. This allows you to use SQL. So this is a more native integration into the database, makes graph technology accessible to SQL developers, and you can use SQL tools and development frameworks. So Oracle Graph is a graph database for the enterprise, and we have native support for property graph and RDF graph models. Oracle Graph is supported in all database editions, in all platforms. In Autonomous Database, you have automated modeling and some advanced features that help you get started quickly. So here are some additional resources. Our webpage, we have several live labs, we have a YouTube channel, we have a blog. So I really hope you will check us out there. And thank you very much for listening. And please reach out to me if you have any questions or comments. And we very much look forward to working with you in the future on a graph project.